So now that we know how to compute the greatest common factor of a set of terms, we're going to use that to factor a polynomial. This particular polynomial is multivariate. It has v's, w's, and y's in its terms. And we want to factor this expression. We want to break it apart into multiplicative pieces using the greatest common factor technique. So what's our strategy? The first piece of the strategy is going to be to identify the greatest common factor between the terms in this polynomial. Once we've identified it, we want to factor it out. What does that look like? Well, after we go through the process of determining the greatest common factor of the two terms, 18v w to the 7th y squared and 24v to the 4th w to the 9th, what we're going to do is use a technique that I like to call multiply and divide. What it's going to look like is multiplication outside a set of parentheses that we draw in, and division on the inside of that set of parentheses that we're going to draw in, with the goal of having that multiplication and that division technically cancel one another out. After all, when we factor an expression, we're supposed to be rewriting it in a way that makes its value completely equivalent to the original. So when the dust settles, we need to have the exact same quantity as we started with, just rewritten in a different way. Multiplying and dividing by the very same quantity simultaneously will achieve that. And then after we've multiplied on the outside and simplified on the inside, we're going to have some dividing on the inside. We're going to simplify by doing the division that's on the inside of the parentheses of powers using subtraction of exponents. So this is one way in which we can see that factoring is really the opposite process to multiplication of polynomials. When we multiplied polynomials, we had to multiply a lot of powers together. And when you multiply powers, you can add their exponents if the bases are the same. But when we factor, we end up doing the opposite process, because where we do all of our simplifying is going to involve a division of powers, and division of powers that have the same base is the same as the subtraction of their exponents. So one step at a time, let's take the two terms that are a part of this polynomial and start by finding their greatest common factor. So between 18v w to the 7th y squared and 24v to the 4th w to the 9th, let's find the greatest common factor of their numerical factors, their coefficients, by factoring them in a tree. So 18 is 2 times 3 times 3. 24 is 2 times 2 times 2 times 3. So how many 2's do they have in common? Well, only one. So there'll be a single factor of 2 in their GCF. How many 3's do they have in common? Well, that's also 1. There's one pair of 3's we can identify here. So the greatest common factor between 18 and 24 is going to be 2 times 3, or 6. Now how about the variables? Remembering that v from the first term has a secret exponent of 1, our shortcut technique is to compare the powers of v and the powers of w and the powers of y from the first and the second expressions, and choosing the ones that have the smaller exponents. So when we think about our powers of v, the first expression has one factor of v, the second has 4. So choosing the lesser exponent, we're going to choose a single power of v for our greatest common factor. At the level of the w's, we're going to choose the w to the 7th over the w to the 9th. At the level of y's, we're going to remind ourselves that our second expression has no y's in it whatsoever, so it has 0 powers of y, which means that we're going to choose no powers of y for our greatest common factor. So there won't be any y's in our GCF. So what is the greatest common factor between these two terms? It's 6 times v to the 1st times w to the 7th. So that is going to be the expression that we factor out of this quantity. So now what do we do with it? This is where my technique of multiplying and dividing comes in. And I can explain it best by saying what we're going to do is surround our expression with a set of parentheses, multiply by this GCF on the outside of the parentheses, while simultaneously dividing by that GCF on the inside. So here's the original, 18v w to the 7th y squared minus 24v to the 4th w to the 9th. Surround it with some parentheses. Take that GCF, 6vw to the 7th, multiply by it on the outside. But I can't just do that because it's going to change the value of this expression, so I need to simultaneously divide. And when I divide a polynomial, I divide all of its terms. That's the distributive property of multiplication over addition in action again, by 6vw to the 7th. So multiply by it on the outside while simultaneously dividing by it on the inside. That's going to ensure that the value of this expression remains the same when all the dust settles. And all we're doing is rewriting it in a simpler way. So now we've done the multiplication and the division. Now it's a matter of simplifying what we have. Because what we have on the inside are two terms which are each quotients, the results of dividing monomials by one another. So the 18 divided by 6 can give me a 3. And then we start looking at the powers of v, w, and y that will help us to simplify. And when we divide powers of a common base, we can instead subtract their exponents. So how many v's should I have in my first term? Well, I have v to the first on the numerator and v to the first on the denominator. And so the number that I have in total of factors of v is going to be 1 minus 1 when I subtract the exponents, but that's 0. So in other words, I have no v's in my first term inside the parentheses. How about w's? Well, same story. I have 7 w's in the numerator and 7 w's also in the denominator. So when I subtract those exponents, I'm going to get 7 minus 7, or 0. So I have no w's in my first term inside the parentheses. Meanwhile, that y squared has nothing to combine with, so it survives. So my first term inside the parentheses is 3y squared. If you're ever in doubt, by the way, of whether something you're doing when you're factoring actually works, you can check it just by multiplying back out. If I multiply these two things back together, I'm going to get 3 times 6, 18. I'll get a v, I'll get a w to the 7th, and then I'll get a y squared. And sure enough, that's exactly the same thing as what we had started with. That's a great thing about factoring problems, is you can always check yourself as you go along just by multiplying out whatever you have, and you should get back to where you started. All right, what about that second term? I've got 24 on top and 6 on the bottom. I can reduce that to 24 divided by 6, or 4. These are nice whole numbers because we got our GCF right. Also, the 3 and the 4 have nothing that they share in common, so this must actually be the GCF. Now, how many v's do we have in the second term? I've got 4 in the numerator and 1 in the denominator. And so in total, dividing powers by subtracting their exponents, I have 4 minus 1, or 3 powers of v. How about w's? I've got 9 in the numerator, 7 in the denominator, and so when the dust settles and I divide these powers by subtracting their exponents, I have 9 minus 7, or 2 powers of w. And so what we have in total is a quantity on the inside, 3y squared minus 4v cubed w squared, which if I were to multiply it by the 6vw to the 7th on the outside, I should get my original expression back. Again, just to make sure that we can sleep well at night, let's check that second term by multiplying it back out. I'm going to have 6 times negative 4. That's negative 24. I'm going to have v times v to the 3rd, and I'm going to have w to the 7th times w squared, rearranging it so the powers of the like variables are near one another. And then simplifying a product of powers by adding the exponents, I'll get 1 plus 3, or 4 powers of v. I'll get 7 plus 2, or 9 powers of w. And I'll have a minus 24 as my numerical coefficient. And indeed, that's exactly what we started with in the problem. Factoring is not the easiest thing in the world to get a handle on. And so using that little check to check your work as you go along is always a good idea if you can spare the time. Now that I've done that, I have some confidence that this indeed is the correct final answer to this problem.